Hello, IBA students of topics in microeconomics. This is my first lecture that I have prepared for you during my quarantine. I'm starting this one with the summary of what we were doing last time in the class. We were solving then for the profit maximizing employment of labor and capital given the production technology and given the prices of output and input. So P is the price of output here, W is the price of labor, R is the price of capital, and P times production function actually gives the value of total production, and WL is the labor cost and RK is the capital cost. So from the total value of production, when we subtract the labor and the capital cost, we get the profit, something that we want to see at a maximum value for which we are trying to find out the correct employment of labor and capital. Now see that in this equation, the profit equation, we are varying both labor and capital so that neither of the input is fixed. This means that we are solving for the long run profit maximization problem. We follow the usual steps because there are two decision variables, labor and capital. We take the derivative of this profit equation first, for example, with respect to labor. So this is P times delta F over delta L minus W equals to 0. So this is the first order condition. Similarly, taking the derivative of the profit equation with respect to capital gives price times derivative of the production function with respect to capital minus R equals to 0. Remember that the derivative of the production function with respect to labor is marginal product. So this is your marginal product of labor. And when you multiply marginal product of labor with price, you actually get value of marginal product of labor. And see that I could have written then this equation as a value marginal product of labor, value marginal product of labor equals to W, or P times marginal product of labor equals to W. Similarly, this is value of marginal product of capital, that is P times marginal product of capital, and we are saying that this should be equal to R. Bringing W and R on the right hand side would do that. Now see that because there were two factors of production, so there are two first order conditions, and because we have two equations and two unknowns, labor and capital, so we can use these two equations to solve for these two unknowns. So we get L star, the optimal labor employment in the long run, as a function of output price, as a function of wage rate, as a function of price of capital. Similarly, the long run demand for capital is a function of output price. It is a function of wage rate, as well as it is a function of the price of capital. Now, while these are the first order conditions that we need to satisfy, remember that we also have a set of second order conditions So let's write them down because I have not written them around here. So let's first write them down so that we do not miss them. The second order conditions are that the that the second derivative on derivative, so pi LL, taking the derivative of equation 1 with respect to labor, we want this to be less than 0. Similarly, taking the derivative of equation 2 with respect to capital, so like writing kk, so this we want to be less than 0, and we also want that this determinant pi LL pi LK and pi KL pi KK, this should be greater than 0. This should be greater than 0. A little bit closer look on these conditions. So first take pi LL less than 0. So when you take the second derivative of equation 1, so this p remains at its place, and then we have FLL, FLL, because there is no L in the second term, so this becomes 0. So we want that P of FLL less than 0, and if we divide throughout by P, so we get FLL less than 0. So see that pi LL less than 0, that is the derivative of first equation with respect to labor equal to 0, demands that the second derivative of the fraction function with respect to labor is less than 0. But what is the interpolation of FLL? FL is marginal product of labor, so FLL actually, remember, is then has to be equal to the derivative of marginal product of labor uh, divided by labor. So this is what is equal to FLL, and so we require that this should be less than 0, means that the marginal product of labor is falling. So when we say that marginal product of labor is falling, so if you are able to recall, in the class we had drawn the average product of labor curve, we had drawn the marginal product of labor curve to see that the second stage of production is between the maximum of average product of labor curve and employment level where marginal product of labor becomes equal to 0. So this is your average product of labor. Let me write it here, average product of labor, and this is your marginal product of labor. So see that this is where you want to be. Marginal product of labor is falling, and it is the employment level between say L dash, where average product of labor is at its maximum, and call this one L double dash, where marginal product of labor is 0. So this is the second stage of fraction. So when we say that pi LL is less than 0, is like affirming that the firm will be able to maximize profit only when the firm's employment level is in the second stage of production. Not only with respect to labor but also with respect to capital, because pi kk less than 0 similarly actually means that the derivative of the marginal product of capital with respect to capital is less than 0. On these same ground, you can conclude this thing as well. So the first condition is that the marginal product of labor is falling, marginal product of capital is falling, and then we have this condition as well, which is like saying that this determinant is greater than 0, and this determinant actually will be 0 if we have like P f of LL minus sorry, not P of LL, it is like P of LL times is like this. Alright, P square F of LL, opening this F of KK minus FLK square. This is something that has to be greater than 0. But dividing throughout by P square actually means that we have to have FLL FKK minus FLK square less than 0. So this term in parentheses should be, or rather greater than 0. So this should be the case. Pi LL is equal to FLL, pi KK is equal to FKK. I have already shown this to you. Pi KL or pi LK is equal to FLK square. See that I have squared because pi KL is equal to pi LK. So these two terms are symmetric because of Young's theorem, and so I can say that this is actually equal to pi KL square or FLK square. So the second order condition, FLL less than 0, FKK less than 0, and FLL FKK minus FLK square greater than 0, that is this term greater than 0. So these conditions must be satisfied around the profit maximizing employment of labor and capital, and if they are satisfied, so at any given price vector, this whatever price, let's say for example, whatever is the price of output, whatever are the prices of labor and capital, whenever we plug those prices into these functions, we will be able to get the long run profit maximizing employment of these factors of production, labor and capital. So the solution to the profit maximizing problem is the set of factor demand functions, long run factor demand function. Now let's move ahead. In the first equation, I inserted the labor demand function and capital demand function. And I took W on the other side, so on this side it was minus W, I took it on the other side, so it became plus W. Similarly, in the second equation, I Also inserted the labor demand functions and the capital demand function, and I switched the side for R, and in this way I am able to get equation number 3 and equation number 4. Now I take the derivative of these two equations with respect to W. So this what that I have done here. See that if I take the derivative of this first equation, equation 3 rather, with respect to W, so let me write it down in the short form. So P remains at its place, and I say that this is dava FL over dava L. I have to use chain rule times dava L over dava W plus, then I have K, so P times, because P will be as it is, dava F L over dava K times dava K over um, dava W, and this uh, dava FL over dava L is FLL, so here we have this one. Sorry, this is here, and similarly I have dava FL over dava K here, and dava L over dava W. So see, this is your dava L over dava W, and this is your dava K over dava W, dava K over dava W. So I have taken the partial derivative of equation 3 with respect to W to obtain this equation, and similarly I have taken the partial derivative of equation 4 to obtain the other equation, which is this one, and then I use these two equations to write down this system in the form of matrix. So see that this PFLL is here, P of FLK has been written here, and similarly P of FKL and P of FKK, and that this dava L over dava W comes here, and dava K over dava W comes here, equals to, so 1 0 on the right hand side, 1 0 on the right hand side, 2, so that I have been able to obtain equation number 5. I use this system, applying Cramer's rule, solve this system for dava L over dava W, and this is like asking the question, what happens when we keep all the other things constant and allow W to change? What is going to happen to labor demand? So when we solve this, so what we will be doing, we will be putting 1 0, because we are solving for dava L over dava W, first element in this vector. So I will be using these this side 1 0. I'll replace it here in the first column, Cramer's rule of course, and then divided by the entire determinant, and that is this one. So dava L over dava W, we have done this in class, is like equal to FKK divided by this determinant, and see that when I look into this. So from the second order condition that we discussed earlier, we know that the term is in parenthesis is positive, that P is positive by definition, and FKK is the the slope of the marginal product of capital, and that because we have already seen that the second order condition requires that this must be less than 0. So we have in this equation numerator less than 0, denominator greater than 0. So dava L over dava W actually turns out to be less than 0. Does it make sense? Of course. Why? Because when wage rate increases, other things remaining constant, production become costlier, and as cost increases, profitability decreases. And this decrease in profitability requires that we should be adjusting the output downward, but adjusting output downward means that the labor should be decreasing. So as wage increases, labor employment decreases. In this long run, at least, this is something that happens. This is something that we have confirmed. It makes sense. Now, when we solve this system for dava Q over dava W, we had done this in class. I don't remember that we were careful enough to put this minus sign here when we were expanding this system, and you better check it in your notes, and if this minus is not around, just put it there. So we have again the denominator is greater than 0. This minus sign is here. F of LK is like saying what is going to happen to marginal product of labor when capital increases. One understanding is that because when capital increases, availability of capital per unit of labor increases, and so marginal product of labor increases with the increase in, it increases with the increase in capital. If this is something that is true, then f of Lk is greater than 0. If it is greater than 0, then this minus sign actually will make numerator negative, denominator is positive, and so this will be becoming negative. What does this imply? That as wage rate increases, capital decreases. If this is so, then we can assume that labor and capital are in the nature of complementarity, so that when one factor of production is decreasing because its price has increased, the other factor of production will also be decreasing. Factor of production, if this is something that is happening, we say that they are complementary goods to each other, or they go together. Labor increases, capital increases, labor decreases, capital decreases. At least this might be happening in some range. If this had not been the case, if if f of Lk had been less than 0, then this term would have been positive, numerator positive, and if that would be the case, then this means that with the increase in wage rate, employment of capital will be increasing, and that will suggest that labor and capital are substitutes to each other, because when wage rate increases, labor decreases and side by side capital increases, so as if the firm is substituting one factor of production for the other. So there is something that is true with respect to the change in wage rate. Now see that when I look into equation 5a, it is the slope of the labor demand function, the labor demand curve, in fact. Um, I have used the same procedure to construct this system 6. So this is something that you have already seen, and in place of taking the derivative of equation 3 and 4 with respect to W, I took the derivative of those equations with respect to R, and I obtained a similar function, and so I had the results like dava Q over dava R, and similarly dava L over dava R. As far as dava K over dava R is concerned, see that denominator is positive, numerator is negative, because this is the derivative of FL with respect to L, and this is like saying that derivative of marginal product of labor with respect to labor is less than 0, and marginal product of labor is falling. And like I explained earlier, there is something that makes sense when we recall that the firm is producing in the second stage of production. So results are not very much different from 5A and 5B. So here on price effect is negative, and cross price effect can be negative or it can be positive. Both possibilities are there. Now I want you to note one thing, and it is that if you compare 5B with 6B, you find that both are identical, and so we can write like for example here that dava L over dava R actually is equal to dava K over dava W, so that we conclude that the cross effects are identical, symmetric. Finally, note that I have combined the system of equation 5 and the system of equation 6 into one system. This is something that is common in both 5 and 6, and see that given this square matrix, in 5 we had this column vector, and in equation system 6 we had this column vector. On the right hand side of equation 5 we had this column vector 1 0, and on the right hand side of equation 6 we had this column vector 0 1. So we can make the two systems into one in the form of matrix. So this is a rather compact form of writing the entire system, If there had been n variables like n factor inputs, then this would have been an n into n matrix. Similarly, this would have been an n into n matrix of the derivatives of the factor demand function with respect to their prices, and this would have been a 1 into 1 matrix, sorry, n into n matrix of ones, that is identity matrix. I have taken here in the second step P common from this matrix. So when it comes out, it is like P square, and this is the rest of the system. And now see that this is the matrix of second derivative of the production function. So this is here matrix of the second derivative of the production function. X in our example include labor and capital in n factors of production. This X will be an n-dimensional vector, and so D2 will be an n by n matrix like we have here. Similarly, see that this matrix has been written in sort of compact form to derivative with respect to the factor prices of the factor demand functions, and so this system then can be written for any n factor of production in this format. I will of course be n into n matrix of ones in the diagonal, the identity matrix. What in the next step I have done is that I have this pre-multiplied this derivative of the production function by its inverse, and you may be able to recall from your matrix algebra that this product should be equal to 1. I have sort of 1 into 1 identity matrix because I pre-multiplied this matrix of second derivative by its inverse. The same thing I did here, pre-multiplied this identity matrix with this inverse of the second derivative matrix on this side, and so the equation does not change, but then see that this is like 1, and similarly when I multiply this thing by this identity matrix I get the same thing. So we get P square equal to the derivative matrix. Here I have missed W, so let me write it down here, W. So derivative with respect to factor prices of the factor demand function, and this is the second order derivative of the production function, its inverse in fact. Because this is negative semi-definite, this matrix is negative semi-definite. We know this because of the second order condition for profit maximization. So its inverse is also negative semi-definite. Here this then implies that this matrix D of XPW is also negative semi-definite. This is one conclusion that we are able to arrive at, that this matrix of derivative of the factor demand function with respect to prices is negative semi-definite. See that if you look closely to this matrix, you will be able to compare it with the substitution matrix that we had seen in the consumer theory. There we had two goods, and we were writing, for example, dava x1 by dava p1 here and dava x2 by dava p2. So in the substitution matrix, these diagonal elements were on substitution effect, and these off diagonal elements were cross substitution effects. So this is something that is in parallel with the consumer theory's substitution matrix, and so you may call it a substitution matrix associated with the production rather than the consumption. Now look into these two equations once again, equation 3 and equation 4, and I have written them like here. This is the previous equation 3 and 4 that we had written previously. Now what I have done here is that I have taken the derivative of equation 3 with respect to p, derivative of equation 4 with respect to p. So see that when I take the derivative of equation 3 with respect to p, so first this thing has been written as it is. I have ignored writing down the terms in the parentheses, but remember that this is like FL and then all the things in the brackets. So taking the derivative with respect to p, we actually make use of the product rule. So first I write this thing as it is, so it is FL. Then I write p as it is, and then take the derivative of this bracketed term. So I have FLL dava L over dava P plus FLK dava K over dava P. Because there is no P on the right hand side, so in the right hand side we get 0. Similarly is true about this one. See that first I take the derivative with respect to P, writing down Fk as it is, this one, and then plus I write down P as it is and take the derivative of Fk using the chain rule. So dava Fk over dava L times dava L over dava P plus dava Fk over dava K times dava K over dava P equal to 0 again, because the equation 4 has no P on the right hand side. And once I have taken these derivatives, I take the FL and FK terms on the other side, and then form the system in the form of matrix exactly on the same lines that we had done previously. So see that this is something we are already familiar with, and that in place of W or R, here we are having P. So dava L over dava P, and dava K over dava P. And in place of 1 0 or 0 1, like that was in equation 5 and equation 6, we have minus FL and minus FK on the right hand side. So I use Cramer's rule to solve this system. First for dava L over dava P, you can check that the outcome is equation 7a. And similarly, when I was writing down the equation dava K over dava P, I put this vector in this second column and then solve the system using the Cramer's rule. We are interested in the signs of delta L over delta P and delta K over delta P. Now, if you look into the denominator, we have already discussed that denominator is positive because FKK minus FLK square has to be positive to satisfy the second order condition. Let's check about the first. Let's check now the numerator. So denominator is positive. Numerator FL is marginal product of labor. It has to be positive. And this is FKK. We know that the firm produces in the second stage of production. So FKK has to be negative, and this negative sign combined with this negative sign to become positive. And that again Fk is the marginal product of capital, and because the firm produces in the second stage, Fk has to be positive. Flk, it can be positive or it can be negative. If it is positive, then unambiguously we will be having delta L over delta P greater than 0. But this is something that will be happening only if we have FLK greater than 0. To the extent that we are willing to believe that this is something true, we can say then that as the price of the output increases, labor demand is going to increase. This makes sense because when price increases, normally it is expected that the profitability is going to increase, and so the firm might decide to produce more, and in order to produce more, the firm will be employing a more amount of labor, and so delta L over delta P is expected to be positive normally. Same is true about delta K over delta P. Here we have FLL less than 0, so minus becomes plus, so first term is positive. And again, if we are assuming FLK or FKL is greater than 0, so this entire ratio becomes greater than 0, and so we have delta K over delta P greater than 0, indicating that as price of output increases, because firm might be producing more, the amount of capital employed will be increasing, and so we will see that P and K moving in the same direction. There is something that normally is expected. Okay, let's move to another point. If we insert the factor demand functions into the profit equation, we get what is known as the profit function. So profit function will be a function of output prices and input prices, and that this profit function will be giving maximum attainable profit at any price vector. This profit function has certain properties. The first property that we have listed here is that the profit function is increasing in output prices, and it is decreasing in input prices. Means that when output prices increase, the profit optimal or maximum earnable profit increases. Similarly, if input prices increase, then maximum earnable profit decreases. This is something that is understandable, because even when we are not we are not changing the output, when output prices increase, because we are not changing the output, then we are using the same amount of input, so cost remains the same. But revenue increases, and this should be increasing the profit. Similarly, if input prices are increasing, and if we suppose do not change the output, then cost will be increasing with revenue being same. But this property actually is saying more than that. It is saying that maximum earnable profit will be increasing in output prices, and it will be decreasing in input prices. We have to prove this property. We'll do this when we move on. The second property that we have is that the profit function is homogeneous of degree 1. This is important. Homogeneous of degree 1 in prices. Remember that when we are saying that it is homogeneous of degree 1 in prices means that all prices, prices of inputs as well as prices of outputs. And it is like saying that if all the prices, that is prices of all inputs and prices of all outputs, change in the same proportion, profit will be changing, or maximum earnable profit will be changing in that same proportion. So if output prices and input prices increase by 10%, this property is saying that the profit will be, or maximum earnable profit will be increasing by 10% as well. See that this is your profit function. Suppose let us write it down like this: equal to P times Y minus cost, say W times L minus R times K. So if price increases by 10%, so this means that this revenue will be increasing by 10%. Similarly, this cost will also be increasing. Labor cost will be increasing by 10%. Capital cost will also be increasing by 10%. So all costs will be increasing by 10%. This means that this difference will also be increasing by 10%. This is what that we mean by this. Let's take a numerical example. If you are still in doubt, suppose that revenue was equal to 1000, and suppose that labor cost plus capital cost was say equal to 600. Now if output price increase by 10%, so this means that this will be increasing, revenue will be increasing by 10%, and it will be becoming 1100. Similarly, if input prices are increasing by 10%, this cost will also be increasing by 10%, and so we will be having 660 rupees of cost. And see that previously the profit was equal to 400, 1000 minus 600. Now it is 1100 minus 660, which is equal to 440. So see that profit increases from 400 to 440. It is like saying that the profit increases by 10%. There is a temptation to think that when both input prices and output prices are increasing in the same proportion, profit should not be increasing. Partly true, in the sense that when you are saying that profit should not be increasing, it is the real profit, because revenue has increased by 10%, so cost of production has also increased by 10%, while nominal profit has increased from 400 to 440. Real profit is still the same. That is that is the uh, profit computed in terms of the basic price is still 400. But this increase in price is because like of general inflation, and whenever there is an inflation, real profit will remain same, but nominal profit is expected to increase at the rate of inflation. So this makes sense. Then we have the third property, which is like saying that the profit function is convex in prices. Means that it is convex in output prices as well as it is convex in input prices. Finally, we have fourth property, Hotelling lemma. We will not be proving this property. Let me write it down only. This property says that if we take the derivative of the profit function with respect to any of the price, then we will be, this is R, so like derivative of profit function with respect to any of the price. Suppose that we take the derivative of profit function with respect to the output price. If we do that, we will be getting output supply function, that is the units of output that will be produced such that these units will be maximizing the profit at the price equal to P, and wage and rental rate equal to W and R. So let me just write these down here as well, W and R. This is known as the output supply function, and we will be discussing this in greater detail later on. So the derivative of the profit function with respect to the price of output gives the output supply function. If there were more than one outputs, then derivative of the profit function with respect to the price of the ith output ith price, output price, will give the ith commodities supply function. This is what that is one part of Shepard's lemma. Similarly, if you take the derivative of the profit function with respect to any of the input price to WR, any of the input price, say W, so you will be getting negative of the 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 factor demand function, that factor demand function of which the price has changed. So like for example, if I took the derivative of the profit function with respect to wage rate, so I will be able to get the negative of the labor demand function. Similarly, if I had taken the partial derivative of the profit function with respect to R, I would be getting the capital demand function, negative of the capital demand function. There are other properties that have been mentioned both in Maskell and in Varian. I am concentrating on only these four properties. They are important to some extent. Let me erase this red portion, and let's see that if we can prove some of these properties. So let's do this so that we have space. And This is like um, cleaning the chalkboard. Let's do that. Okay. Okay. So let's start proving these properties. First one is that the profit function is increasing in output price and decreasing in input prices. In variant they have provided a combined proof by simultaneously increasing the output price and decreasing the input prices. We are doing it separately to avoid any confusion. So our proof actually will be having two parts. Let's call part A as the one associated with the fact that profit function is increasing in output prices. So let's start with a price vector P such that at this price vector we are producing uh, net put vector um, which is profit maximizing. So this is P times Y. So Y is the profit maximizing net put vector at the input output price vector P. Now suppose that price vector changes from P to P dash such that P dash is equal to greater than P. It is greater than P in output dimensions and equal to P in input dimensions. So this strict inequality holds for output and equality holds for inputs. If we multiply both sides by y, scalar product, so that we have p dash y, this must be greater than or equal to p y for the reason that the net put vector is same on both sides, that on the left hand side we have P dash which has higher output prices um, relative to P and same uh, input prices. So P dash Y actually has associated greater revenue than at Py with same cost, and so this is something that is true. But of course, when price vector is P dash, Y is not the profit maximizing net put vector for this price vector, that for price vector P dash, if we want to have maximum profit, so it will be associated with the net put vector, rather net put vector y dash. So this is something that is now maximum profit at P dash. So this means that P dash y dash, that is when you are producing y dash, when this is your net put vector, then your profit must be greater than or equal to P dash y, because at P dash y is not the profit maximizing net put vector. P y dash rather is the profit maximizing net put vector. So we have P dash dot y dash equal to greater than P dash y. but see that here we have p dash y greater than equal to py. So just to bring this down here, py, don't forget this dot, remember this, and from here I have p dash y dash equal to greater than py, so that we can conclude that pi p dash is greater than or equal to pi p, given that p dash has a higher output prices relative to p, and both vectors have same input prices. So this is with respect to output prices. Let's now prove that profit function is decreasing in input prices, that is, as input prices increase, profit decreases. Again, start by assuming that pi p is equal to p dot y. So y is the profit maximizing net put vector, and let there be another net put vector y dash. So we can write that py dash is to be less than or equal to py, because y is profit maximizing, so any other net put vector, any vector other than y is not profit maximizing. This is what that we have here, but then y dash definitely is profit maximizing at some price vector. Let it be p dash. So I have p dash y dash being profit maximizing at so y dash is profit maximizing at p dash, and this is what that I have here, p dash equal to, okay. Given this statement, now I want to write another one, and it is that p dash y dash actually has to be less than or equal to p y dash, and we need to reason that why this is so. These net put vectors are same on both sides. The price vectors on the two sides are different in input dimensions. So because p dash has same output prices as p, so this means that revenue on this side, on the left hand side, is equal to revenue on the right hand side, but input prices on the left hand side are higher. So this means that the cost on the left hand side are higher, and so we have for same revenue more cost on the left hand side relative to on the right hand side. So this conclusion, let me write it more cleanly, that p dash y dash is less than or equal to p y dash. But then py dash is also equal to less than p dot y. So I can write that from here that py dash actually is less than or equal to p dot y, and when we combine these two, the conclusion is that p dash dot y dash is equal to less than p dot y, or by p dash is less than equal to p of pi of p, when the two price vectors are same in output prices, but p dash is higher in input prices relative to p. And see that this is the argument that we used here. Without this argument you won't be able to reason efficiently. Just make sure that you have the understanding of this. Netput vectors are identical on both sides. Output prices are identical, so revenue is identical on both sides, but on the left hand side we have higher input prices relative to on the right hand side, so the cost must be higher on the left hand side. The revenue minus cost must be lesser on the left hand side relative to on the right hand side. And then we combine this thing with this equation to arrive at the conclusion that p dash dot y dash is equal to less than p dot y, so that as input prices increase, maximum earnable profit decreases. Let's now start the proof of property 2, which says that the profit function is homogeneous of degree 1 in prices. This means that if all the prices increase in same proportion, the profit will be increasing in that same proportion. Or if all the prices decrease in the same proportion, maximum earnable profit will also be decreasing in that same proportion. Remember again that when we say all prices, that means both input and output prices. Start again with the profit function. P is the initial price vector and y is the net put vector that maximizes profit at this price vector. And this actually is like saying that p dot y dash is equal to or less than p dot y for any net put vector other than y, that is y dash. Profit is less at price vector p. Now if I multiply both sides by a scalar quantity t greater than 0, so the left hand side becomes t times p of y dash equals to or less than t times p dot y dot is to be here as well. So this is like saying that if y is the profit maximizing net put vector at P, it must also be the profit maximizing net put vector at T times P, because right hand side turns out to be greater than the left hand side. So y still is the profit maximizing vector, and this is like saying reaching the conclusion that by TP actually, which is equal to TP times y, or T by P is equal to T P y. So if all the prices increase in the same proportion or decrease in the same proportion, y is still the profit maximizing net put vector because of this condition. So we say that profit function is homogeneous of degree 1. So like we saw in the example that when we increased the prices of inputs and output by 10%, profit increased by 10% from 40 to say from 400 to 440. So this was easier than it looked. So the other one, the third one, is important. It is important in terms of meaning as well. You should be able to understand the meaning of this third um, property, that the profit function is convex in prices. And again, when we say prices, that means output prices as well as input prices. First, write down the mathematical definition of convexity. Let there be two price vectors, P and P dash. Alright. Given these price vectors, define their weighted average. Say for example alpha P plus 1 minus alpha P dash, and call this weighted average P double dash. So there will be one net put vector which will be profit maximizing with this price vector, call it y. There is another net put vector which is profit maximizing with this price vector, so call it y dash. And there is one net put vector which is profit maximizing at price vector p double dash, call it y double dash. So let me write it down. We have pi p equals to p dot y maximum profit, earnable profit at P by P dash equals to P dash dot Y dash, and finally by P double dash by P double dash actually is equal to Y double dash Y double dash Y double dash. So I have not forgotten this time the dots. Now let me consider this part, in fact right hand side of this part. So I can write P double dash dot Y double dash actually is equal to alpha P plus 1 minus alpha P dash. So this is your P double dash, and we have P double dash dot Y double dash, maximum profit. Now I want to open this bracket. So this is a vector. I'm talking about the dot product again to alpha P dot Y double dash plus 1 minus alpha P dash Y double dash. So I have opened this bracket, and now I have, because of this equation, I have rather, just a minute, I have P dot Y double dash. This must be less than or equal to P dot Y, because at P, Y is the profit maximizing net put vector. So at P, any other net put vector should be giving a smaller profit. And because this is true, I can multiply both sides by alpha. Similarly, now I am using this second term. I know that P dash Y double dash, so P dash dot Y double dash, this one Y double dash is less than or equal to P dash Y dash. Why? Because at P dash, Y dash is the profit maximizing net put vector. So with Y double dash, the profit should be less relative to at Y dash, when P dash is the price vector. Okay, now I can finally write using this equation, the last one, multiplying both sides by 1 minus alpha. So 1 minus alpha p dash. So I multiplied this part by 1 minus alpha y double dash, and this is equal to or less than 1 minus alpha on this side, 1 minus alpha on this side, as well p dash y dash. Okay, next I add these two together on this side as well as on this side. Okay, this is what I am doing. I am adding left hand side into left hand side, and this right hand side into this right hand side. So alpha p dot y double dash plus 1 minus alpha 1 minus alpha 1 minus alpha times p dash y double dash. So these are these left hand sides equal to less than the right hand side. Write down the right hand side now. Alpha p dot y plus 1 minus alpha 1 minus alpha p dash y dash p dash y dash. Okay, now I am taking this y double dash out on the right hand side, so that I have alpha p just a minute. Okay, so I have alpha p plus 1 minus alpha p dash y double dash dot y double dash. I have like recreated this thing on the left hand side equal to less than, this is alpha, and this is pi p plus this is 1 minus alpha, and this is pi p dash p dash. But what is this? This is pi p double dash or pi alpha p plus 1 minus alpha p dash is equal to or less than alpha pi p plus 1 minus alpha p rather pi p dash. So are you able to get this? What this is saying is that the profit at the weighted average of P and P dash is less than equal to the weighted average of the profit at P and P dash. So this is the profit at average price. This is the average of the profit at P and P dash. So profit at average price is less than or equal to average of the profits at the prices used in the weighted average. So this is something that is the definition of convexity, and I want to give a sort of graphical explanation of this thing. So let me first erase this, and then let's look into the property using some sort of graph, and the proof is easy. Graph is rather easier to get the idea that what actually this property is saying. It is important, of course. So let me first erase every of these things. When you are taking your notes, make sure that you have not missed any dots in the scalar product that you are computing to obtain profits. So it's sufficiently clean. This is the last one. Okay, this is done. You will definitely be hearing these sounds in the background because I'm not in a controlled environment. There's a lot of traffic around there. So let's see what actually is the meaning of property 3. First, in terms of output prices. So let's first talk in terms of output prices. Output prices. Like we are saying that the profit function is convex in output prices. I want you to understand the meaning of this graphically. Alright, suppose that we have plotted profit along the vertical axis. So this is pi, and P along the horizontal axis. Now draw the equation pi equal to P y minus pi equals to y minus WL minus RK. We have only 2 dimensions, so I am like in this equation keeping y constant, WL, RK all are constant. So see that when P is equal to 0, I have the intercept minus WL minus RK. Here it is, and that this right hand side, this is the intercept. It is linear in P. Y is the slope. So y, see that P is changing, y is constant. So if It is like saying that if we find P the price of output increasing. So suppose that this was your first price, call it P1, and this is your second price, call it P2, and this is like saying that as the output price increases from P1 to P2, your profit will be increasing even when you are not changing the output. So even when you are not changing the output, when price increases, total revenue will increase because you are not changing your output level. So this means that you are still employing the same amount of labor and same amount of capital. So your costs are not changing. But revenue is increasing because P has increased, and so profit will be increasing even if you are not adjusting to take advantage of not adjusting the output and input to take advantage of the increase in output price. So there is something that will be happening. You will be moving, for example, from this point to this point if you do not change your output. But because the output price increases, you definitely will want to change the, the output. You know that this was your profit at price vector P. So at another price vector, your output, this output vector cannot be profit maximizing, and so you'll be changing your output vector with the result that profit will not be increasing from here to here. It will be increasing to a greater extent. So see that your optimizing behavior is telling you that you will not be moving. If you do not optimize, if you do not do anything, so see that this is what that happens. You move from say profit equal to pi 1 to profit equal to pi 2. This is happening when you are not changing the output, and so you are not changing the inputs as well. This is the increase in profit, but because price has increased, you will reconsider your production decision and your employment decision, with the result that your profit will not be increasing to pi 2, it will actually be increasing to a further extent. And so I should be seeing a behavior like this. It is like saying that the profit is increasing at an increasing rate, not at a constant rate. It is increasing at an increasing rate. Why? Because with the increase in P, you are also adjusting your output. If you had not been adjusting your output, the profit would have been increasing at a constant rate. But because you are adjusting your output, so profit will be increasing uh, at an increasing rate. Similarly, if the prices had gone down of the output, and that if you keep on producing the same amount, revenue will be decreasing and you will be moving here. But then because you will be acting optimally, so profit will not be decreasing to this extent. Profit will be decreasing, but at a sort of decreasing rate. Why? Because you will be adjusting your output to the reduced price, and so your profit will not be falling linearly. It will be decreasing at a decreasing rate. This is what that we are saying, that the profit function is convex. So this is the behavior of the profit function, and this is the red line is representing the behavior of the profit equation. So you may want to write this, that this is your pi in the equation, and this is your behavior of your profit function. So this is optimal behavior being traced, maximum earnable profit along this. This is the linear behavior representing this equation, profit equation. You should be able to learn more clear about the difference between profit function and profit equation. Alright, let's now talk in terms of input prices. Let's clean this mess up. And this time, along the horizontal axis, we will rather be plotting the input prices rather than the output prices. Along the vertical axis, however, the profit along the vertical axis we are still plotting the profits. So let's talk in terms of input prices. Okay, prices. Pen is not working. Again, write down the profit equation. Pi equals to P y minus WL minus R K. So I am now keeping this thing constant. I am keeping labor constant, and I am keeping this. And then I am saying that what happens if W increases. So if let me write it like this first, so that you are not getting confused. So I have Py like a constant. I am now writing minus R K. We are not going to touch any of these, minus WL. I am not going to touch L as well. But then see that this is something that is to be greater than 0, because this is revenue minus the cost of capital. This is cost of labor, and there's something that is happening when labor is equal to L bar. So if I now plot this equation, this time see that what it will be saying, W is here and pi is here. This is like saying that if W increases, labor cost will be increasing, and this term minus labor cost will be decreasing, and so profit will be decreasing linearly, because W is having a linear relationship. So I have a sort of downward sloping profit equation this time. Remember that in the last graph it was increasing because P was adding to the revenue, and so it was adding to the profit. Here it is decreasing because W is adding to the cost, and as cost increases, profit decreases, and so we have a falling behavior of this equation in the input prices. Now this is your W1, suppose, and at W1 suppose that your profit is equal to W. Oh, sorry, your profit is equal to pi 1. Now wage rate increases from W1 to say W2. If you still keep on producing the same output, if you keep on employing the same amount of labor and same amount of capital, then you will be moving along this linear track and you will fall here. This is your pi 1 and your profit falls down from pi 1 to pi naught. So this is the decrease in profit. Linear decrease happening when you are not adjusting your output. But if you adjust your output, then this means that you will also be adjusting your labor and capital, and this means that your profit will not be falling from pi 1 to pi naught, but to a lesser extent. And by lesser extent, like for example, it might come here. But if this is something that is happening, so then this means that your profit function actually is moving like this. And then this is a sort of convex behavior. Got that? So profit function is convex. It is falling, but not as great as to represent a constant. Decreasing at a constant rate. It is decreasing at a decreasing rate. Why? Because when input prices are increasing, you are not just sitting around doing nothing. You are adjusting your inputs as well as your outputs, and when you are doing that, the drop in profit is not from pi 1 to pi naught, but to a lesser extent, somewhere between pi 1 and pi naught. So profit decreases to a lesser extent. This is what that we mean when we say that the profit function is convex in input prices. So profit function convex in output prices going like this. Profit function convex in input prices going like this. And this convexity property will be returning soon when we are dealing with some other aspects of our discussion. So just this is not the end of the convexity property of the profit function in prices. There is one application of it. We'll be seeing it when we proceed further, but not here, of course. A little bit later. Now the hoteling lemma. I understand that I have already told you the meaning of this. That in this hoteling lemma talks in terms of the derivative of the profit function with respect to any of the price. If the price is output price, so then you will be getting a supply function. If the price is an input price, so you will be getting a factor demand function. So this is something that I have already stated, and I don't need to repeat it now. This is what that I had written earlier, minus L, which is a function of price of output W and R. So derivative of the profit function with respect to input prices like wage is the negative of the labor demand function, and derivative of the profit function with respect to the output price gives you the output supply function, and I have told you already that if there are more than one outputs, so then I will be putting the I subscript to indicate that which output price is changing, and I will be getting the ith output supply function. Remember that this output supply function gives the profit maximizing output at any given price vector, where price vector includes both input and output prices. So this is the Hotelling lemma.